So last week we discussed about general control systems, like how to build a PID controller, right? In Simulink, MATLAB Simulink, and I sort of gave a recap for you all to recall whatever you had done early in MATLAB, like how to create a basic block diagram model, how to create a closed loop uh, control system, how to implement a PID controller, then tune it. Then after that we covered the Siegler-Nichols method, the Siegler-Nichols process of tuning a PID controller. We used the auto-tune method first, then we use the Siegler-Nichols method. We discussed what sort of steps we follow to tune a PID controller using the Siegler-Nichols method, and then using those parameters to tune a control system. So when we were discussing about the Siegler-Nichols method, I discussed about some of the advantages and disadvantages. And one of those was that one of the disadvantages was that it was not very robust. It was not very mathematically, complete. It's some you just use the trial and error method to find the KP, right? Then you use the KP as your critical gain, and based on that, your critical gain, your critical period, everything is based on whatever the KP value that you get by guessing using trial and error to obtain your system in marginal stability. But you want your system to have this marginal stability to use this Siegler-Nichols method. You can't use it, right? We discussed, we sort of used an example, and I showed a system where you can't have a marginal stable occasion where you can't use the Siegler-Nichols method, right? So today, now in the earlier lab, we discussed about generic control system, right? It necessarily don't have any other disturbances or any of that sort, right? But what if there's some sort of a disturbance in your system? Can we use the same method? Can we use the Siegler-Nichols method? So if you all remember, we didn't have any disturbance in that system, right? We didn't have any sort of disturbance in that system. So we didn't have any sort of disturbance in the earlier system. So yeah, that was okay, right? Okay for us to use whatever the method that we used. But by any chance, if we have some sort of a disturbance, then we have to change the method that we tune our control system, and also sometimes we might have to change the controller, the strategy that we use to control the system, right? Yeah. So now, I will just slightly remind you some of the theory that you all have done under this part. So basically, I'll ask some questions. So I think you have your exams in another 1 week, 1.5 weeks time, right? So so as a revision, so let's say you have some disturbance in your system, right? You have some disturbance in your control system, but how many ways are there which you can use for disturbance rejection, and what are those ways? What are the ways that we have? I think this might have been covered since this is lab 2. I think it must have been covered in the middle part of the semester. So any idea how many ways at least, or you can name one method? So you all have to talk now. Usually when I do labs for the Mala Bay campus people, I ask questions, naming them, and they have to answer, right? So I'm not going to do this because I'm not sure that you'll be comfortable with that. It might be after work and also, yeah. So generally there are three methods, right? So there are three disturbance rejection methods that we use when designing control systems when there's some sort of disturbance. So to mitigate calamity to the disturbances, we use the three methods. That's the first is the feed forward plus feedback control system, right? You use the feed forward system along with the feedback control system. Then you have the ratio control, and then finally you have the internal module control or the IMC control, right? So in the feed forward controller, like along with the feedback control, it's the coupled one. You have to have two conditions satisfied. So in the first is that you need to measure the disturbance, right? The disturbance that's there in the system should be measurable, and sometimes this might not be practical for some control systems, especially industrial control systems. This condition might not be practical where you can measure the disturbance. So if you can't measure the disturbance, you can't use this control type, right? Have you all done anything called controllability, observability in control system?
No, sir.
No, right? Okay. So yeah, then second method is like second condition is that the feed forward controller should be realizable, right? So sometimes that's also not like not available in feed forward control systems, and also like so always the feed forward system should be coupled with a feedback controller. It can't be an open loop system. And also like the disturbance does not affect the system's open loop transfer function, right? So it does not affect this closed loop system stability. So these are some of the notes that you will have to remember for the feed forward. We are not going to discuss for the feed forward. Then there's a ratio control that also you can like read the theory, but what we are like focusing here is the internal module control, right? Internal module control. Can't you see the screen? Someone has put a message saying screen is not visible.
Oh, sir, we can see.
You can see that. Right. So we'll be discussing about the internal model control or the IEMC method, right? So so basically the IEMC control model uses an assumed process model, right? So basically the difference between a process output and a model output is that this set to like a set point. So I will like draw the basic the scheme, the block diagram of we call this IMC model so that you can get an idea. So basically you have like this is like a theoretical model. You would like a practical understanding of what this is when you are doing it, right? So you can like here. So then that's the plus here. GC here. So you have to find all these values, right? You have to find GC, GP, and GM when you design the system. I'm just trying to like I'm going to explain the theory here. I just want to like draw the block diagram so that we have to like construct something similar when we are like modeling it to a practical control system. Like, right? So we add in the disturbance here. The disturbance we could like use it as D. So then we can have the output as Y. Then we could like get this. So to that we need to add another. We need to get the G from here. I'll try to make it short, right? So I'll be just wasting time on theory that has already been covered. Plus, can like reduce this, and we have to give this as a feedback here, right? As the error, so disturbance. So this is actually this is plus, this is plus. So this is generally the basic block diagram format of a IFC, right? So so if there's no disturbance here, then the modeling error, so which is EMT, it's this one, the function of time. So it will be 0. There's no disturbance, right? So you can like check your notes and find what the generic equation is and all these things. Right? I'm not going to write this. Write all this take a little bit of time, so you just have to check your note. So we are going to implement something like this for a practical control system. Now, I don't think you have done some sort of practical scenario. You might have just taken the control system. You might have derived the equations for this for GCS and all. So we'll try to approach this to a practical problem, right? So we'll look at a practical problem. Right? So we'll go here towards our notes once again. Right. So here now what we have is like a tank, right? So you all have done tank model. So if I ask any questions, can you all answer? Give me a second. Hello, sir. I'm sorry, I got a call from Rosanigar. So yeah. So I most probably I will get the password reset today, so I will be able to upload this recording today, right? Okay, so we were at the tank, right? So now tell me. So if we get a tank, do you know how to model a tank? A tank using differential equations? Do you know? So okay, you just imagine this is your exam
Yes, sir.
question, right? How do you do it?
Balancing masses.
Yeah, we'll start like this. So let's say you have a cylindrical tank. You have a cylindrical tank. Let's say the radius is 4 meters, right? And let's say now there's water leaking from this at 40 cubic meters per second. Right? So how do we approach this? Like, okay, so how do we now? We have to find out. Let's say this there's a height here. So we have to find the rate of change of the height. How do we approach it? So this is very simple. How do we approach? So this is how we like. This is the basic step before you go for a tank question like that. How do you do something like this? We have to find the rate of change of height as the water flows out. How the height changes. These you should be knowing now. You are a final student, so these are like first year maths, actually A-level maths. So the rate of change of h, right? So what we need to find is dh over dt, right? So now we know v, right? We know that the volume, the rate of change of the volume, we know dp over dt. It's 40, right? I just this without this. So so we can, so of any object, we know the volume v is equal to what? The area of the base times h, right? So area is this. Okay. So now from this we can find dv over dt, right? dv over dt. You find this. Now you can see now here the variable is h. Now a is constant. Variable is h. So we can't differentiate this directly by dt. So we use the chain rule of differentiation. You can like differentiate dv over dh to h over dt, right? So this would give us a into dh over dt, right? So we know the area here. So an area of a circle is equal to pi r square. Right? Pi r square. So we could like get dh over dt as so r here is a constant. Here r is not changing, so it's 4. So 4 squared. So 5 the constant. 4 squared is 16 dh over dt. Right? So what they are asking for is the rate of change of height. So we need this. We can like isolate that is equal to, so this is dv over dt, dv over dt, dv over dt divided by 1 over I6. So now in this case, we don't have an issue. We know dv over dt, that is 40. We can substitute it here, right? So that's there. So the result is 40 divided by I over 60. So if you like simplify this, you can get somewhere around, I think 1640. So it's 5 over 2, right? This is the base. So I just wanted to like remind you this, so that's how we approach a tank. So now we'll approach the tank, the control system, like it's like you call this I think you all might have done this for your controls one. You call this the capacitance, like hydraulic capacitance, right? So we have a tank like this, a tank like this. So let's say that input rate of flow. So that's the input rate of Q1. We can write this as a function of time. It is important. It is important when you write differential equations, especially if you don't have now. In earlier case, we didn't have to go to the differential equation because they had given the dv, right? So if not, what we would have got is something like this: dh over dt equals a dv over dt, right? Sorry, dv over dt dh over dt, right? So in this case, we can write this as a differential equation d dot equals a h dot, right? So now this is a differential equation. So now we can, so this is in a time domain. So we can write this function of time. So we can get the Laplace of this. Now we need this part here. So that's why that's so it's important that you write in what format, in what this thing, whether it's in the time domain or like in the spatial domain, right? So at the time, it's height here. So height is also a variable, right? As the flow changes, the height changes. So you can write as a function of time. You can get the radius of this part as r, and you can like get q2 as a function of time, right? Now these things you should be good at, because now when you have the final exam, you could like get a question like okay, so just imagine you get the same question for your finals where you had to like model an IMG control for this case, right? So okay, so there's the tank here. So this is the input, this is the output, this is the radius. So someone can you tell me where we can start? Where can we start from your knowledge up to now?
Excuse me, sir.
Yes.
Sir, R is R is the resistance, right? So yeah, R is the resistance, right?
Yeah. Resistance. Yes. Sorry. What is resistance? It's the resistance for flow. Yes. Sorry. Okay. Not the radius.
Oh, okay, sir.
So yeah, what can we like modify? Yeah, you tell me. How do we start now? So basically, we could like get the change, like so the volume is changing. So if there's an input here, there's an output here. So based on this, we can like get the volume change, right? So rate of change of volume, we can get like dv over dt as q1t minus q2t, right? This is one relationship that we can get. One. So then we can get the earlier equation that we got. We can get dv over dt. We can like expand it. We know we can get the area, like the area of the the bottom of this. We can like neglect this part. We can get the area of this as a. So we can like get dv over dt equal to e over dt a into h. So we can get the relationship as a dh d over dt. So this is the second relationship, right? This is what we derived earlier for the cylinder. Now you can see that this and this are equal, right? These two are equal, so we can like get 1 equals 2. 1 equals 2, we can get it as q1t minus q2t equal to a Is my handwriting clear? I'm using the mouse, so I'm not sure whether it's clear. If it's not clear, let me know. Okay. If any part is not clear, is it clear, Nipun?
Yes, sir, it's clear.
So
Yes, sir.
we can get this relationship, and also like if you all have done basic fluid dynamics, you can like get the rate, can get the resistance into tau. Right? So this is like this we can like get as the relationship. This is 4. Right? So these are the basic equations that you need if you are required to model a tank like this, right? You are required to model a tank of this sort. This is all you need. So if you want, you can like make a note. I mean, you can watch the recording. I mean, this with simple things. I think this from your first module of control system. So we just need these. If you are given a tank, so we just need these relationships to like model it, right? So it's quite simple. So now let's go to the tank that has been given. So in this tank, we can use the same way. So we can get the relationship for, I'll write somewhere here. Right. So I think that's the first part, right? Yeah. So you have been asked to derive of the mass balance differential equation in this tank. And we have to get this format. We have to get HS over US because that's what's equal to GPS, right? So so we have to model it accordingly. So we model it. So I'm not sure whether it will be we have enough space. But I'll start from here. So the relationships that we derived earlier, V equals H. So dV over dt is equal to A dH over dt. This is one. Just check whether these variables that I'm using are correct. Right? This is one. So this is one relationship. Then we'll get the other one. We can get dV over dt equal to, in this case it's Qy minus Q naught. This is 1, this is 2, 3. We can get this. It's the output is Q naught. So the height is HT. So we can put HT as the resistance is R. And get this as the radius, sorry, resistance into Q naught. So we have 3 equations here. So what we can do is we can get this equation. We can get this equation over here. So we can write. We can get this equation here. We can write dV over dt equal to Q1 minus. So we can substitute Q naught from here, right? So here from here we can derive Q naught equals to HT. Q naught is Q naught, right? Q naught equals to naught over R because we have to develop this format, right? So we need H in our equation, we need Q in our equation. So whatever the stuff that we don't want here, we'll try to reduce. Right? So we can model this as Q naught. So we can substitute Q naught. We can substitute this part to here, right? So we can get here H over. So we can like HT, right? HT over R. Now what we can do is we can take Laplace, right? We can take Laplace of this. So if we get Laplace of this Yeah, yeah. Before we get Laplace, we can. Before we get Laplace, what we can do here is, yeah. I mean, we can write this in the format. We can substitute this part here. We can substitute this here, right? If not, we'll just get Vs here. So once again we'll have to like do this. So we want the Hs, right? We don't want Vs, we want Hs. So if we get Laplace, we'll get Vs. So we can substitute this here. And we can get A dh over dt equal to, can you all see? Shall I use the whiteboard? I'll write here. A dh over dt equal to, so we have q I here, qi minus, so we have ht over r. Right? So we can get Laplace now. So now we have what we need here. Right? We need h and q. Right? We need h and q. So we have h and q here in this. So if we get Laplace here, what we get is as this is okay. As hs equals q I s minus hs over r, right? So so now if you like do like simplify this, you can like get the format, you can get the rs this thing, and you can try this out if you want. So what you get is hs over r, hs over q is right, qis actually. This is qis what you are getting. Q is equal to you get r a r s plus 1, right? So now we have got this relation. We have got the relationship that they have asked us to get. Now, but we can't just take this. Now here, can you see that there's a delay, right? So there's a delay. So actually what you are getting is qt. There's a delay of theta. And then after the delay of theta, you are getting qi, right? So this we can write this as, this with the delay we can write it as this qit is equal to q. This is actually the time is t. So you give a delay of sorry, it's qt, you delay it by theta. This is equal to q by t, right? We can write this as t minus theta, right? We can write this as this. So now if we get Laplace of this, we get Laplace for this function. What we'll get is qis. This is q, okay? Does it look like q? Q is equal to qs. There are still students coming. I don't know whether they'll be able to understand this. So please watch the recording if you miss any steps, right? and get the Laplace of this. You get in the exponential form e to the minus theta. Expect these things you don't have to memorize. You will be given a Laplace table for this. Right. So now we have got this. So what we can do is we can go and substitute this. So we can go and substitute this q1, so sorry, qy to this qy, right? Because we want it in the format of q, not qy. They have asked us to get in the q. They have asked us to get hs over qs, not hs over qis, right? So we have got a relationship for qs. Qs is here, right? So qs is the q is here. Q is here, qi is here. So if you get if you model it for this, and if you get this equation is wrong. What we got earlier for qis, this is now this is what you get relationship with this. This part you get here is the relationship between hs and qis. If you write this in your paper, you will get some marks, but it will not be enough. It's not the final answer. So they ask you to get qs. So what you get is you get the relationship for qis with respect to qs, qt with respect to qt minus theta. You get the Laplace of it. You get it in this form. You substitute that here. Then you get the equation. Where shall I write it? I'll write it somewhere here. So yeah, I will write the final this thing what you get from this here, right? What you get from here after you substitute here is hs over qs equal to, here now it's theta, right? So it's equal to re minus theta s over a rs plus 1. So this is the equation, right? So this is the answer for the first question. Now you don't do the same thing, you do it by yourself, right? So I'm not going to keep it for long. So you can get the answer in this format. So this is what you need. And so to model this, we will yeah. So you write it somewhere. So we will use for this we will use values. So we need for us to do the approximation, we should have integers. We can't use variables and do this. So to do the approximation, we'll use values where r is 2, right? So if please note it down somewhere. So you will need this. You will need the values. That's all the workings. The values have not been given for the in the lab sheet for your approximation, but you will need it for you to do the approximation, right? You need it to do the approximation, right? So there was some students who came just now, so you might wonder where I got this. So watch the recording if you miss some parts, right? So you use these values. You use r equals to theta is equal to, let's say, 4, then a is equal to 10. Okay, these values, okay. R is equal to 2, theta is equal to 4, a is equal to 10. You can like try these. If you want, you can try this for some other values. If you like want to try the system for some other values, it's fine. You have the liberty to do that, but please specify what the values you use, right? For this part, this is the answer. For the first part, this is how you get the answer, right? hs over qs, you get it in this format, but for you to do the approximation, you need integer values. So you can use whatever values you want for r and theta and a, but for this example, we'll use this, but you can use same values if you want. If not, you can use different values, but make sure that you don't write whatever the workings that I do in the lab, you have to do it on your own, right? If not, it's just useless. I mean, like, it's not pointless. So we'll use that relationships and those relationships, those values, and we'll write our equation, which we'll be using for our earlier step, right? So I said that R is equal to 2, right? So we'll write it. So we can get Hs over Qs as 2. So I said theta is 4, right? 4s divided by ns plus 1. So this is actually what you get for GPS, right? GP in the GP form of in the spatial domain or this domain, right? So we have that. So now they ask us to like first order response time consider of 1 minute is required as the output. Design an IMC controller for this system with the pair approximation for the exponential term. So now what we'll do is we'll get the system with the approximation and without the approximation, right? So so you can like do this. So I will make the system together as one. So so you can like when you are doing it, you can like do it together as I do, or you can like do it by parts. It's up to you. So if I talk about the pair approximation, so there's 1-to-1 pair approximation and 2-to-2 approximations, right? We will discuss while we apply the approximation to this, we will discuss how we do it, right? So now we have got the equation for this model, right? So this is in the form of this. In the form of this. So do the workings. I will get a whiteboard. We get the whiteboard. So much more easier, and it's easier for you all to see also. Right. So now what we got earlier was we got Hs over Qs was equal to, we derived the differential equation for this. So guys who got late, you can watch the video on how we derive the differential equation for this. But I will write the answer. So it was R E minus theta the domain divided by A area R S plus 1. Now we substitute the values. Substitute the values. So we got R as 2, E theta as 4, S area as 10. So get it as 10. Is actually so R we can, the resistance we'll get it as 1. I couldn't give the resistance, right? So resistance will give it as 1. So altogether we can consider this as 10, right? Altogether it's as 10. 10 S plus 1. Right, so we can get this equation. Now we have this system. So this is basically what we get here is like it was GC, right? GPS, right? This GPS. So from GPS we need to get GMS and GM plus is GM minus. So this is basically GPS. So let's get GM plus is basically the numerator, right? So we will get GM plus you might have done similar theories, similar workings for your like more detailed workings for your theory. This is not actually, this actually should not be done in the lab. This is something that you should like do in this thing. We should basically consider only on the simulating thing, but I'm just doing this as like a, so that you can understand what we're doing, right? So GMS is basically the numerator, right? So numerator, we can like get the numerator in E minus 4s. We can put, so numerator as in like the, what do you call, the exponential on the argument. So we can get this here, right? Then GM minus, we can get this part, right? So we can model this as a transfer function. 2 over 10s plus 1. We can model this as a transfer function in Simulink. So from these two, we can get the IMG controller. We can get the IMG controller GCS. I will use another color. Use another color for this. What's the color? So GCS. This is a theory. You will have to memorize this. I'm not sure you are given any equations or whether you are used to memorize the equations. So the GCS is given by 1 over GM minus S into 1 over B S plus 1 the power of R, right? So if we substitute the values here, so 1 over GM minus S is this. So this is upside down, right? So this you have to like flip around. So this is GM minus, this GM minus. So to get 1 over GM minus, you have to flip this around. So what you get is 10s plus 1 over 2. Then here actually we use tau as 1. Okay, tau d is equal to 1, right? So we can use 1 here. Tau d is equal to 1. So we can guess 1 over 1 s plus 1. How do we decide the R value here? How do we decide the R value here? Can someone answer? Can someone answer how we derive the R value?
One.
How is it 1? Why is it 1?
To make denominator and numerator.
Yeah, right. So yeah, for a system to be stable or a proper system, just to be to make it a proper system, the numerator and denominator's orders have to be equal. So in this case, it's R is 1 because it's first order. It's all first order, so R is equal to 1, right? Good. So you know your theories. So we can like simplify this. Get in the format of 1 over 2 10s plus 1 divided by s plus 1. Right. Now there's something called a paired approximation that we use here. So the approximation is this. So the approximation has two forms, right? So we use the approximation on an exponential, right? So if I divide, sorry, so you can get the approximation. So it's approximation. So we have 1 to 1, 2 to 2, right? So the one-to-one pair approximation, what you do is if you have e to the power minus theta s, you can write this as 1 minus theta over 2s divided by 1 plus theta over 2s, right? The one-to-one one. I'm not sure whether you have done the two to one, but I'll do it just for your reference. You will not be using this. 1 minus just like that. You write the same thing. Right? You write the same one-to-one one. You make it second order by adding there's a huge deriving for this. This is like approximation method. So you have the pair approximation, you have the Taylor series approximation. You just different ways where you can like use this. So these are all what mathematicians do. They use certain approximation methods. You can they derive so many methods, and they just tell us, okay, so you get this. So we just use it, right? They derive these and they show us that these. So you can write this as this. So we just simply use that. That's what we do as engineers. So as an example, now in this case it's 4s. So we can write that. So to the minus 4s, we can write this as 4s. So 1 minus. We'll use this. Okay. So just forget that. Forget this. You don't have to think about that. We'll use this. So what do you write here? So it's theta is 4, right? So theta divided by 2 is 2. 1 minus 2s, 1 plus 2s, right? So we can write this as, so if the minus 4 is equal to our gm plus s. So we can write, instead of this, for gm plus, we can write this. So that we can go and substitute to here now as our gm plus. When you're getting the sorry, now we have to when you're getting when you're modeling it in this what do you call this simulating, we can use this. Now in the first scenario, we don't have to use the approximation. We can model it without the approximation, right? So without the approximation, you can use just this. You can use this here, this. Without the approximation, you can use this. Right? With the approximation, you can you substitute this and use it. So I don't have space here. I'll have to clear all this. Right. So with the approximation, so we can write e to the minus 4s. We derive it to be 1 minus 2s plus 2s. Then so we can substitute this to our general GPS, right? We can put this into our plug into our GPS, and from our GPS we can get our GM plus and GM minus, right? So if you get GM plus and GM minus from this, now you can do the working, right? I'm not going to do the working here. So if you get GM plus here, if you want me to do the working, let me know, please. Okay. Just drop the message in the chat saying that you want it to be done. So GM plus is equal to 1 minus 2s, because it's just this. the numerator. Generally, because there's an exponential here. Right? So gm minus s equal to now here if you like look at the equation what we got earlier, it was 2, and I'll just do the working, so it's like 3 to the minus 4s 10s plus 1, right? This was our function. This was our GPS, right? So this we broke down into this, right? So we got this as our gm plus. So this part goes to the bottom, right? So we can write gm is equal to 2 over 10s plus 1, because they are from the beginning, this part, and this part which came from the approximation Give me a second. Sorry, my lab දෙවෙන්නේ. මොකද ඒක? Sorry? හරි මම PC ඔයාගේ මේ මම දාන්න එක. ඔයාලා අද රැවි දාන්න. මම ඔයාලට 3 නෙමෙයි මම 4 වෙනකන් කල් දෙන්න right? හරි. To get this plus part from here, 10s plus 1, then get 1 plus 2s. So now this is gm minus, right? So basically what you have to do is now we need to get similarly we need to get GCS. This is once again equal to that, equal to 1 over gm minus s d s plus 1 r. This is with the approximation, okay? Earlier what we did was without the approximation. This is with the approximation. So by substituting here, we know gm minus s, this is equal to this. You flip it around, so you get 10s plus 1, 1 plus 2s divided by 2. Then you get this part that is equal to that is 1. So we get s plus 1. Now what's the value we put here? R. What should R be here? Here now it's the second order system, right? So R has to be 2. Now we can we got this equation. Now we can model this in our Simuric. Now, so if I summarize all the equations that we got, right? So if I summarize all these equations I got, so we can write without approximation. Without the approximation and with the approximation. Right? You also like when you're making this, it's better if you make a chart. You have to like submit a handwritten report as well, so you can like get the equations after derive, summarize it, because you have it's sometimes confusing when there's GC, GP, GM, everything. It's very confusing. So if you like summarize it down to like basic parts, it's easier for you to model this, right? So here we got GM plus s e to the minus 4s, right? GM minus as 2 over 10 plus 1, 10s plus 1. So you got GCS minus 1 over 2 10s plus 1 divided by s plus 1. These are all the equations that we need without the approximation. We get the same things with the approximation. We get gm plus. Now in this case, you can't have an exponential here using the approximation. Gm plus is equal to 1 minus 2s. Gm minus is equal to it's I think 2 over 10s plus 1 1 plus 2s, right? GCS equal to, so you get that, you get 1 plus 2s. You flip this around, 1 plus 2s, 10s plus 1 divided by 2. This 2 comes down. Tau d s plus 1. So tau d is equal to 1. So we get s plus 1. Since this is second order, the numerator is second order. To make it a proper system, we make it square. So, okay, now what we have to do is build a Simulink model using these values, right? So, tell me, like, can you like simply build a Simulink model using this? In these, can you just simply build a Simulink model? First of all, tell me, are you all with me? Are you all like catching up? Can you all someone answer?
Yes, sir.
You all get it, right? If you have anything
Yeah.
unclear, please let me know, right? So you can like discuss. You know, this is not supposed to be a one-way delivery. This is supposed to be a two-way delivery. So I accept you all to like I expect you all to like try it with me and like let me know if there's any doubts. Like in this case, this was just basically some general simplification. So you can like go over it, and when I'm doing it, you can like tell me if something is wrong, right? So yeah, so like if you look at it, you look at this now. If you are similar with, if you are familiar with Simulink, so sometimes it might be a bit bother for you all to like. Now this is in the transfer function format, right? Now this is in the transfer function format, but now these are in the zeros and poles format, right? Now when you are going to like plot these, sometimes it might be issue having a coefficient for s, right? Having some sort of a coefficient for s like this sometimes could be an issue. Could be some sort of a bother. So we can like remove this. So in this case, we can like get GCS. To do that, what we can do is we can take 10 out of this, right? This part we'll take 10 out. So we'll have s plus 1 over 10. 2 plus 1. So we can cut this off and we can get 5 plus 1 over 10 divided by s plus 1 is equal to GCS. Now this part, now here you can see there's a 2 here, there's a 10 here. So now this is also like trouble, right? To have all these things. So what you can do is you can take 10 out of here also. Right? You can take 10 out of here also. So if you take 10 out of this, you will get 1 over 10. plus 105. Yes. So it's this here plus 1/10. Now here we are getting a coefficient twice, but we'll ignore it. Now we can like use this now. If we have like two coefficients here, that's going to be an issue. But in this case, it will not be that much of an issue, right? Just one coefficient, so it's plus one. That's plus one. That's plus one square, right? Now we'll model this in our Simulink, right? These values. These values we can line our Simulink, right? So sorry, this is not 1 over. This is yeah, that's 1 over. Right. Okay. I will model this in Simulink now. So we'll write Simulink. It take a little bit of time, right? If you have any questions, you can ask now. If you have any doubts or anything. How long is your paper duration? Final exam?
2 hours.
2 hours.
Yes.
Is it like
2 hours.
online?
Yeah.
Right. So we'll create a blank model. So I will create one model. So we for this particular case now, so we should like derive the step function for this, right? So we'll assume RT equal to 5 and dt is equal to 3. So we get our step function accordingly.
Sorry, can you share?
Sorry?
You're not.
Sorry. We get step function from here. So we'll get these. We'll get RT is equal to 5. So the input trigger input function and the dt or the delay is equal to 3. Right. So like that. Use the step time here. Step time. So step time is equal to 3. Finally, we'll give us 5. Now we'll first implement the system with the approximation, right? So with the approximation, I have set down my functions that I use. Give me a second. I've deleted the whiteboard. So I think the function that we got first was this now. You once you're doing, you can like check this. So basically you have to like change some just if it's something has been displayed. Uh, so I think it was this format. Is I think it was, yeah, I think it was this format. So basically what we can do is can get a 041 continuous. Continuous. Can get a more bit. We will get 041. So we can use the values. We have to get the. So if you are planning to build this transfer function 5 s plus 1 over 10, apply x plus 1. So we can build it. So we can put the gain now first this one gain p5. The bottom pole is +1 is +1, so it has to be just -1. So and the numerator has to have a 0. It should be a +1 no then, so it has to be -1 okay. You apply this, you will get that format. So, right. So we get that. That's there. So we need to get the GM minus. The GM minus is, you can like refer the block diagram of your building when you're building it, right? GM minus is equal to 2 over 10 plus 1. So we will that. This without the approximation. Okay. So we will get the transfer function from here. I'll just type this has to be in the form of 10s plus 1. Basically, it has to be 2 over 10 plus 1. Numerator is 2. The bottom we have to have 10 and 1, right? If you apply this, you get it, right? So now let's create the model. We need a time delay. So the transport delay of transport delay will put this set the transport delay. So we have here using the paid order. So it has to be 1 because we're using the first order. Even without the approximation, you can put that, right? Time delay, we'll put it as 4. I think the time delay is 4, right? What we have been given. So you can use that accordingly. Get the time delay done here. Right. I'm building the first system so that you can just copy paste whatever you all have there onwards to build the system that's given in the block diagram. Right. So we need this like this thing to like get the output. We'll get a thing from here. We'll get the scope to measure this, and at the same time we need to plug the. I think there's a requirement where you need to plug all the graphs in one graph, so we can in the M script, so we can get this thing out as well, right? So yeah, so this is now we can build the system without the approximation using this. With the approximation you can build this. So So we have to use the 1 over s plus 1 as well. We have to use the 1 over s plus 1 transfer function here. So we can get it from here. Get the transfer function here. It's a continuous one. Transfer function. All right. So now let's do the routing. By the way, I just wanted to ask, have you all done PCB design? Yeah, of course.
Yes, sir.
I had done. Right. This is just like how you do the schematic wiring. So we'll put a step function for this transfer function. We need a multiplexer to add this. So can get the multiplexer from top here. We can have this here. And give the first transfer function. We can give the step function here. Basically, we will have to give the same function what we gave here. So it was step time 3 and final value 5. Right. So we have to give this to this one. So we have to add this what we get from here. So we need to once again we need to add the multiplier here. Summation block here. We need to get the feedback, right? So, so we need to get the feedback from from this through. I think that's how the block diagram was, right? So with the disturbance, yeah. So yeah, we'll have to add this once again. So if you are not understanding, you can so basically you don't know how we got the function. We are just substituting the functions to the block diagram of the with the approximation without the approximation. Right? This is without the approximation. So you all have been given the block diagrams. I'm not sure whether you all have derived how to get the block diagrams, and it's not necessary because they have already developed the control system and they already have given you a block diagram. So you just need to what you need to do is you have to find these values. You need to find the GCS, the GPS, and the GM minus and the GM plus, and you used to be able to substitute the functions that you get into this block diagram that you get. Right? That's all. So I will get the CMOUT cell. So you get this. Whether we run out of time, I try to simplify this. Okay. We need to create 3 controllers, but we'll do somehow. Has to be negative. So we should get this from here. We need to so there should be a multiplier, right? If I look at the block diagram once again. So that should okay. Yeah, there should be another one, right? Right. So I get another one. I need to get the output from from here, then I have to get this from here. Sorry. With this block, right? Now this one, this is particle. If there's no error, this is 0. But since there's an error, give it as the feedback. Right. So our system without the approximation is correct. I'm not sure whether I gave all the step functions or not. Give it back. Simulate and see what we get. Small delay, right? I don't know what's wrong. We'll check that in the end. So that's 5 plus 1 over 10 plus 1. This see that 5. We will first create the architectures and then we'll check what the error is. Right. We'll check. We will first create the architectures of this and see what the error is in the end. So now this is with the approximation. Now we will create one without the approximation. Right. So without the approximation, we got the functions. We'll use the same. You get this, you get a 0 pole order here. Continuous. Get 10. We're trying to build this, right? Yeah, trying to build 10 plus 1 over 2 s plus 1 over 10 divided by s plus 1 square. So I put the values here, s plus 1 has to be minus 1 over 2 minus 1 over 10. Poles has to be minus 1 minus 1, right? Squared s minus s plus 1 squared. So the poles has to be 1 plus 1 s plus 1. And the gain has to be this integer 10. So I think we get it, right? Or 2 s plus 1 over 10 s plus 1 squared. We'll build the transfer function. Sorry, not transfer function, the control system without the approximation. What's wrong? We need to get the input signal from that itself. I'm trying to do it a bit quick because we're running out of time, right? Last time also I got some additional time from your. We'll be using the same function as this one. Right. So we'll be using am I correct? So it's same function, right? Yep, it's the same. Keep the block diagram in front of you so it's easier for you to like do when you're on. Node +2. Let's do OS +1 here, then can same transport delay with the order set to 1. Then you need an adder. For the adders first part, you need to get the same disturbance from a stop. That is from here. Then you need to get the feedback loop. Feedback loop you have to create from here. Then another add operator here. What we can do is we can so create the feedback loop. We need another transport delay plus another GM. So do this and this. I'm just doing a lab for you all, right? This is not actually not supposed to happen. You all have to try this alone, but I hope you all will try this alone. Usually use different values without using the same words, but in this case I use the same one. But don't, I hope you all, I mean, I can check that when you are doing. Please don't, please try by yourself, not use it. Because I'm going to give you all time until your exam is over, right? For this lab. This lab you can submit after the exam, second one. So please try this for yourself. So here you are getting from here, then you have to do this here. So get this input and you're going to give this as a feedback. Right, so I think this is with the approximation. And now we'll build a general control system like with the normal PID. We used the normal PID control system with the auto-tuned PID, right? The one we built earlier. This is actually now this you should know. I mean, this is very simple. Same thing that we built earlier. PID, you have to do the GM plus here. We have to give the disturbance, the transport delay. We have to give the disturbance. So with the disturbance, the same one we gave earlier. You can connect it from here, right? Make sure that when you are doing it, like try to do the wiring properly. I mean, the routing properly, because I'm like in rush here. You can like you will have enough time. So you'll be done with the exams and you will have enough time, so you can take your time and do it, right? Let's skip out here. So we can give this output will be Right. So not sure that I have like made any mistakes while doing this. You all can check when you are doing this, right? These are three isolated systems, okay? Just like these are not the same system. This is not the same system, okay? So you can like see that I have just given the same input to all these and the same the disturbance to all these. If not, these are all isolated systems. If you want, you can like build this system once again, again and again. Like you'll have to just give the step input independently for all the systems, and you will have to give the disturbance independently to all the systems, right? But this is much more easier. But if you want to do it, you can do it. If it's much more easier for you to understand that way, it's fine, right? Right. So if I will see if this is working, whether there are any errors. Not sure. Yeah, so we are getting something like this. Now I will increase the time to 100 and see. So whether the control is quite good or what. Yep, we are getting some sort of a steady state. There's a delay. Then after some time we are getting a steady state without the approximation. Then with the approximation, I think we'll have to plot these in one graph and see how it's working, right? The PID, it's we can tune this. We'll tune this. The general PID can tune this using the auto tune method like we did earlier. Any questions you can ask, right? Anything unclear? You can ask. Don't just do it for the sake of doing, right? So you guys are electronic. You guys are doing electrical and electronic both, right? So hands up, people who are like focusing on electronics. Like I mean, you all are like majoring in electronics and electrical. I know, but I mean, once you all go out, yeah, you might be focusing on electrical. Some people might go to electrical. Some people might go to electronics. So just hands up who wants to go to electronics. I mean, in the so I can get an account. Are there people who wants to go to electronics? I hope you guys are listening to me, right? But useless.
Yes.
Yes, sir.
Yeah, just can you hands up so that I can like this is just general information. This looks fine now. We get the steady state, we need it a little bit fast. I think anyway there's a delay here, right? So with the delay, we can't make the thing very accurate as well. So we have to make it a bit robust. So when we make it like robust, then there's a chance that the system, yeah, so that's the thing. So there's overshoot, there's undershoot, but I think this will do, right? So we'll update this with this KP, KIKD parameters. I think this is the last lab I'm doing, so that's why I just asked the question. So basically, there was like two people raising their hands. I think the majority are planning to go to electrical side, right? It's fine. So now, if you are planning to go to electronics, you will actually like extensively need the control systems, and even in electrical side as well. I think you need controls, and I'm not actually familiar with the electrical side, so I'm sure. But electronics, of course, you need a lot of control systems which are going to process control, robotics, or like you know unmanned aerial vehicles like UAVs and all. So a lot of things that you need controls, even heat, like energy systems, like thermal systems. You need. So yeah, these are the values. So just understand about the principles, like a very interesting area. There's a lot to learn. You will like if you are planning to like go into higher studies, or into if you are like planning to work in a industry related, if you're planning to work in an industry that's related to control systems, then you will like learn a lot. Like, it's very interesting, and it's a very new. I mean, it's quite old, but it's a very volatile area. It's updating every day. There's new stuff coming up. So yeah. Okay, now we have update the system, right? So now we'll try to plot this all the graphs together. So to plot all the graphs together, we'll get these outputs as y y1 and y2. Okay. So and so we need a clock, right? So we are going to plot these with respect to time. So we need the clock. So we'll get a source here. We'll give it. We'll give another this thing as this as T out or something. T. Right. So I think the system is complete. Now we will save this. We'll save this. We'll save this as lab 2. So now we have the Simulink model. So now we can plot all these graphs and see, right? So basically we have got y. Y is the without the approximation. Y1 is with the approximation, and y2 is the general PID tuned one, which we manually tune. I mean, automatically tuned according to our preference, right? So we can compare all these and see how the outcomes are, right? So don't forget that this PID control we tuned with a delay of touch on 5 seconds. So along with that, we'll see how the system is. Right? So we'll go to MATLAB, the M script. We'll get a new M script. So now what we have to do is we have to write the code to get the plots. I think you all have. So we'll clear we'll plot the. Now when you're plotting, right? You're plotting. We have to get the whatever the like now. You see the T is 1 by 1, right? Same format matrices. So it's 1 by 1. I mean arrays or matrices or whatever. So it's T and y1 and y2, right? We'll plot T y and we'll give the color. Let's say we have RGB, right? So we'll just give this one R. We'll copy this. We'll get T with respect to y1. Give this in green. We'll give with respect to y2. Give this as blue, right? Right. So we got this, and now we have to like give the legend, so it's easier for us to understand. Legend. So in the legend, what we need is we need so red is the general IMC without the approximation, right? IMC without Then we have next we have green. IMC with approximation. And then we have blue, the general PA. Right, so now let's plot this. I think it's right, okay. There's some sort of an error. I think it's T out. Time series, here is the time series service. You give the T out. I'm not sure whether it's T out or T service. You see T out and C. Actually, that's the issue. Something is wrong. I saved the I have to run this. I think I didn't run this. I have to keep this running. Right? Run this, and now I think it's T. To run this, and it has to be T now. T gave properly. Uh, I don't know what the issue is. I have to check this. Right. So anyway, if you like plot this, if you like plot all this together in one graph, you'll be able to get you should be able to see this, right? So yeah, I'm not exactly sure what the error is, right? I will check and inform you all, but I think some we probably something with me naming the stuff. So anyway, if you plot all this together, you should. I will try to get all this to one thing. I'm not sure it will work. We'll see. I just want to show you all like in one diagram how it looks like, but I don't think it will work. Right? So it's you don't have a scope where we can plot them. So, getting stuck. Yeah. Anyway, I'm not also sure what the exact issue is. It's a very simple code, but we'll see. Anyway, this is what you all have to do. Just check what the issue with the code is, and I will, if I get time, I will inform the batch chef what the issue was. But now it's we don't have enough time to like do this, right? So anyway, what you can do is you can build this thing, and you can have to plot all the graphs in MScript, right? You can like use the same code, but make sure the variables are like properly defined, right? Whatever the issue is, right? So right, if you are having any other questions apart from this, or have any issues or any unclear points or anything that you need to clarify, if you have, you can always contact me, right? If you have any issues, I will figure out what the issue is and I will inform the batch step where the issue was. Basically, the code is the same thing. The code you don't have to change anything. Just that I think somewhere when I'm like I will show you an example where I have done so that I can understand. So with this step,
Sir, when is the lab one submission?
lab one submission is on the third evening. That's what sir said. I wanted to get both the submissions after the exam, but sir wanted the one before this thing. So I think we will have to use that. But this one, of course, you can like submit it after the exam, right? Lab one, you have to submit it.
Sir, excuse me, sir.
Yeah.
Sir, can you extend it up to at least 5th?
5th.
Yes, sir.
Yeah, I'm okay with it because I just have to mark the lab reports. I can mark it later, but I will confirm that with Professor Miguel and let you know, right?
Okay. Sir.
Yeah, I will inform you tomorrow, right? Most probably
Okay.
it will be possible. It will be possible. If not, you just yeah, it's fine. Then you submit on the 5th. It's fine. Can you submit it
Okay,
on
sir.
the 5th, like not midnight at around 5 o'clock maybe? So that I could like start marking. If not, okay, it's fine. Then what's your usual deadline? Is it midnight?
Yes, sir. It is better if
Yeah,
you
yeah,
can
okay,
make
okay,
it.
okay, right. You submit on the 5th midnight. Fine. Okay then, guys. You all don't have any questions, you can leave. So make sure to like take your time to do the lab, right? You can like understand the concepts and do it. For the guys who missed the lab, the initial part, yeah, we like the theory and all for the tank modeling and all, you can like watch the recordings. I will send the recording. I most probably will get your like Moodle access by today. If not, I will send the recording just like I did today to the batch, right? Right. Okay, then guys,
Okay,
you can
sir.
leave. You can leave.
Okay, thank you, sir.
Good night.
Good night. Bye.
Good night, sir. Thank you.